Okay, now let's take a look at the last three questions. Okay, so for the section 10.12, yes, uh, this one is still about the difference of two population means, but here we know these two population standard deviation, or say population standard variance. So we know sigma 1, sigma 2. And then what is the parameter of interest? The parameter of interest is still the difference in two means, right? Here mean two population means, here the mean fill volume. Okay, so we have two machines, and then okay, so we could specify the null hypothesis and the alternative hypothesis as this. So here, this one is equivalent to say, okay, mu1 minus mu2 equals or is not equal to 0. So that's the mean difference, right? So here, the hypothesis value is 0 for the mean difference. And we have the information we got. And then we calculate the z statistic. And of course, this is a two-sided test. That's why we have two critical values, negative 1.96 and positive 1.96. Since our observed test statistic right here, right, is between these two critical values, is not in the rejection region, so we fail to reject null hypothesis. For the p-value method, and then this is two-sided test, so the p-value is going to be 2 times the probability, right here. 2 times capital Z greater than 0.988. That's how from the Z table you could get this number as the p-value. So our p-value is way bigger than 0.05, so we fail to reject the null hypothesis. And then the last one is for confidence interval. So for the alpha equals 0.05, right here, so our confidence interval should be 95%. Okay, that's why this Z is still 1.96 here. And then we plug in the values, that's the two ends. And then since 0, this hypothesis value right here, is not in this interval or not. Of course, it's in it, right? Because the lower end is negative, the upper end is positive. So 0 must be in it. That's why we do not have enough evidence to reject null hypothesis. And the part 6 is about how to do it in R. How to do it in R, we have to use a command which is the z test, dot test, okay? And this is, excuse me, from package BSDA. And then we import the data into the R, and then we specify this X and Y, these two. Basically here, machine 1 and machine 2, okay, on this table. Yes, we just import these two columns of numbers into R, named as Z1, Z2, just variable names. And that's how we're going to use this code to do this two sample Z test. Here mu, that's the hypothesized value, right? The mean difference is 0. That means mu1 equals mu2 if the null hypothesis is right. And then confidence level is 95%. We have to specify this sigma x and sigma y right here, these two numbers. And we would expect the numbers from the R, you can see right here. That's the Z values, right? Statistic value. So we got by hand is 0.988 here, got more digits. P-value exactly the same. And the confidence interval, yes. See? And here they specified x1 bar, x2 bar, okay? So we also did this in the note, in class, in the notes, okay? So please go ahead to check. Make sure you know how to use this Z test to run the test. Please get both, okay, either by hand or by the R code. Okay, for 10.212, this is still about the mean differences of two population means. But now we do not know the population variance anymore. Okay, you see we have club 1, club 2. And in this case, because we do not have any information about the population variances or population standard deviations, then we have two ways, right? Remember, we have two cases. Please check the notes. One case is about we assume these two population variances are equal, and the second case they are not equal. Of course, equal case is easier. Okay, so here, what are the estimates for mu1, mu2, sigma 1, sigma 2? Because we do not know any of those four population parameters, but we do know have these two variables, right? The samples. Then obviously we just use the sample counterparts to estimate the population parameters. That's the whole idea we have been adopted for the whole semester. So x1 bar, that's x1 bar, right? So this is estimated for the mu1, x2 bar for mu2, the mu1, mu2, that's the estimate. And then how about S sigma 1, sigma 2? They are population standard deviations, right? Then we can use what? Sample standard deviations. So this is S1 estimated for S1, sigma 1, S2 estimated for sigma 2. Is the evidence that the coefficient of reinstitution is approximately normally distributed? So, because remember, for these two sections, right, we always if you check the notes, right, so we always say those two populations are from the normal parents. Okay, so they are, and then in the real practice, that's the number we got. You never know whether those numbers are from normal or not. So that's why, and also these numbers, we do not have that many. Some of you may say, what if we can do the histogram? Yeah, histogram does not work well when the number of observations is not that big. That's why we have to use the QQ plot. We just QQ plot these two variables here, two samples here, see how it goes. So you can see for club 1, club 2, most of the time we would not expect those dots. Those are the theoretical quantiles and the sample quantiles exactly along this blue line, okay? But as long as they are kind of close enough, then we would say, yes, we could just say the samples are really from the population parents. That's the idea, from normal parents. So here, they are kind of close. That's why this normality assumption passed, okay? From the normal plots, which show that most of the points spread out closely around the line, we can say the normality assumption is satisfied. Here, we do not need to be that strict. Okay, cool. Yes, this is the code about how to get this QQ plot for both club 1 and club 2. All right. So is the assumption of equal variance satisfied? Yes, because we do not know the variance, right? And the population variance. So it's very natural to say which category we're going to use, equal case or not equal case. So here we use the criteria, say, because we do not know any one of them, we only know sample 1. So whenever this one is between, the ratio is between 0.5 and 2, we would say sigma 1, sigma 2 are equal. Okay. This is kind of a rule of the thumb. All right, in our case, actually it's 1.24, which is less than 2, is in the range, right? That's why we say the equal variance assumption is satisfied. So under the equal variance, then we could have this so-called pooled version of the standard deviation SP. Okay, this is the formula to do it. Okay. After we get the SP, then we get SE, right? Use this little sp times the square root 1 over n1 plus 1 over n2. This is about this big. So we're going to use this one a lot of times. See, first confidence interval, we have to use SE right here. Right, plug in the numbers. And then for the test, yes, you see the null hypothesis and alternative, and then see this t-test, t-statistics. We have to use SE also right here, this number. All right, and the p-value method, yes, because we observed, right, observed this test statistic, right, this one. That's how the p-value is defined. And also I want to say something about degrees of freedom, because this is pooled t, right, paired t. This df equals what? n1 plus n2 minus 2, okay? That's how here we got 22, because n1 and 2 both are 12. And then 12 plus 12 is 24, and then minus 2 is 22. That's how we get the degrees of freedom is 22 right here. Okay. And for the p-value, this is pretty much like the chi-square case. You know, for the t distribution, we could either use the t-table to get a range, the same idea here, okay? Or just use the r to get exactly p-value. Either way will help us to make the conclusion fail to reject null hypothesis, right? Because our p-value is bigger than the alpha value, 0.05. And how to do the test by the confidence interval, because that's still the same rule. If the hypothesis value is in the confidence interval, in our case, you see negative, positive, so 0 definitely is in it, right? Then we fail to reject by the so-called, since 0 is in 95% CIs, we do not have enough evidence to reject null hypothesis. Okay, how can I run this whole thing in R? That's the code. Here we have to specify first sample, second sample, and then alternative is two-sided. Mu, this is hypothesis value, right? Mean difference is 0. And we have to specify equal variance true or not. Paired here is false, right? It's not. Equal variance, that's yes, because what? Because as we explained right here, because the ratio of the two sample standard deviation is between 0.5 and 2. Then we could just use this equal variance assumption. All right, now let's talk about the last one. So this last one is about paired t distribution. So for the paired t distribution, that's very similar to the two sample t, but here you can see those two observations, they are what? They are paired, or they are related, because they are just two measurements on the same observation unit. Okay, that's the difference. As for detail, please refer to the lecture notes. Okay, so we have 12 programmers, and we ask each one of them to write a code in 2 different languages, and then record how many minutes or hours, right? This is the time. Yeah, in minutes. Okay, so, and we want to know whether there is any difference among these two means, these two population means, right? That's the same idea. So here, of course, is the assumption of the two samples are independent and reasonable. Here, of course, these two samples shouldn't be independent, right? Because you think about the same programmer, even though in 2 different languages, but if he's good in one, it gets a higher chance to be another one also, right? So this speed of the coding depends on a lot on the program itself. Okay, we have many examples like this in the real life. For example, like for the swimming, we want to know whether this kind of high-tech swimming suit will gonna affect the swimming speed. Then we just use one swimmer to try to swim like for 100 yards with two different swimming suits and see whether there's a significant difference among these two speeds. Here, same swimmer swim for 100 yards with two different swimming suits. Of course, these two numbers are related because they are from the same program, same swimmer. Here is the same thing. This the time for coding, both 17 and 18, they are from the same programmer. Of course, they are related. You could not just say these two are independent, right? If you say independent, that does not make sense. So this is the whole idea of the pair T. Then for this case, obviously, this assumption that two samples are independent is not reasonable. Functions are coded by the same programmer. What is the estimate for the difference in mean coding times, mu1 minus mu2? So in this case, the mean is still the mean population mean population difference is always estimated as what? Sample mean difference. Okay, so we just say, okay, we first get the difference of these two languages, right, and then take the mean of that. So here we gotta be careful. So here we could just say, we have two ways to do it, okay? Let's back to here. So one way, you just get the difference, the DI, and then you say here, 17 minus 18, which is -1, 16 minus 12, which 14 is 2, and then 2, and then 3, all the way down. And then you just say, you put the DI as what? As the workhorse, we're gonna keep working. So this mu D hat estimate is gonna be 1 over n DI, right? But from the math, this one actually exactly the same thing as 1 over xi, x1i minus 1 over n x2i. So basically it's here the what? x1 bar, x2 bar. What does it mean? You can get the mean of the first one and the second one, sample mean, and then use the mean difference. The same thing, okay? All right, but here I just use the first way, okay? Because I get the DI first and then get the mean of the DI. That's the D bar. So the D bar is 2/3. What is the estimate of standard error of the difference of two sample means? So here, yes, here you have to get what? The standard deviation of the DI, right? This is the DI, standard deviation of the DI. Now construct a 95% CI on the difference in mean coding times, D bar plus, yes, this is the T, okay, and -1 as D. So basically, for the paired T, is just a T for what? The differences, right? So this is actually the T test for difference. Okay. Based on that, we could get the confidence interval, and also we do the test. This is the T test, right? Null hypothesis. There is no mean difference. Alternatively, yes, there is. And then rejection region method or critical value method, you have the T statistical value, which is in the acceptance region, actually is not in the rejection region. So we fail to reject null hypothesis. P-value is the same idea. Fail to reject also. Explain how by the part 4. Part 4 is about what? Confidence interval our hypothesis value is in it, so we fail to reject the null hypothesis also. And then the last part is about how to run this whole thing in R. So you import these two samples, right? And then specify alternative is two-sided, mu is 0. And here, very important, the paired equals true, okay? That's for paired T. You can see that's how we got this whole thing. I hope this video will help you to prepare for your final exam. Please let me know if you have any questions. Thank you. Bye.